In section 5.6, we're going to talk about a specific application of double integrals, and that is computing mass, center of mass, and moments of inertia. So first of all, I'm going to start by defining mass of a lamina, and that word lamina is just talking about a two-dimensional object, so you can think of it as something like a piece of paper, so something that can be drawn in the plane. So if we have a lamina that is in the plane region R with a continuous density function rho, then to find the mass, we're going to integrate the density over the area of that region. So here's an example. Let's see if we can find the mass of the lamina bounded by y equals e to the negative x, y equals 0, x equals 0, x equals 1, and our density function is rho equals 2y. So density of this object increases with the y values. So first thing I'm going to do, as always, is draw a picture. And so this is the picture of the region that we are considering. So I drew the function y equals e to the negative x. And then y equals 0 is my x-axis. X equals 0 is my y-axis. And then in blue, I have that line x equals 1. And so I've shaded in the region that we're talking about in purple. Okay, so what we're going to do then is we are going to integrate over this region I've drawn our density function. So I'm integrating my density function, which is 2y, and I'm going to choose to set this up with the dy first and then the dx. So the y values in this object always start at y equals 0 and always stop on that exponential function. So my bounds of integration go from 0, y equals 0, to y equals e to the negative x. And then for the x values, we're starting at x equals 0, and we're stopping at x equals 1. So this integral is going to give me the mass of the region that I have shaded in. So I'll start with my inside integral. Antiderivative of 2y is y squared. And then I'm going to plug in my bounds of integration. So I get e to the negative x squared, and then technically it's minus 0 squared. I didn't write down the 0. But e to the negative x squared is e to the negative 2x. So that's what I got for my inside integral. And then I'm going to integrate e to the negative 2x from 0 to 1. So let's see, antiderivative e to the negative 2x, and then we have to divide by the negative 2. That's my chain rule backwards. And then I'm going to plug in those bounds of integration. So I plug in the 1, I get negative 1/2 e to the negative 2. And then I plug in 0, so minus a negative 1/2. And there's my final answer. I could put that into a calculator if I wanted to convert that into decimal. I don't feel like pulling out my calculator, so I'm just going to leave my answer as mass is negative 1 over 2e squared plus 1/2. All right, so if we want to find mass of an object, we have to integrate our density function over the area of that object. This idea can be extended into 3 dimensions as well, and we'll see that later on in this video. But if you have an object in space, a 3-dimensional object in space, you can find the mass by integrating over the volume of that object, so with a triple integral. All right, the second application I want to talk about are moments. So these are moments of mass, and moments of mass describe the tendency of an object to rotate about an axis. And I think your physics class can probably do a better job of describing exactly what these mean. But for our purposes, we are just going to talk about our, I'm abbreviating it as m sub x. This is our moment of mass about the x-axis. So this is going to describe the tendency of the object to rotate about the x-axis. And then our m sub y is our tendency for our object to rotate about the y-axis. So to find these moments of mass, I've got two different integrals. Basically, we're integrating y times density. So essentially what we're doing is we are integrating basically our distance to the x-axis, which is y times density, over the area of the region that we're interested in. And then for our moment of mass about the y-axis, it's really similar, except we're integrating x times our density over the area of our region. So those are our moments of mass. And one reason that moments of mass are useful is they can be used to compute the center of mass. And the center of mass, you could think of it as if you wanted this lamina, this object, to balance perfectly on a point, where would you have to place it? That would be at the center of mass. And so our center of mass is defined to be our moment with respect to y divided by the little m right there is the mass of the object. And then moment with respect to the x-axis, again, divided by mass of the object. All right, so again, you will talk about these in your physics classes. I really want to focus on computing them, doing the calculus. And so let's do an example. Let's see if we can find the center of mass of the exact same object we worked with in the previous example. So we've got this lamina that's bounded by y equals e to the negative x, bounded by the axes x equal 1, and we've got that same density function rho equals 2y. So I'm not going to repeat computing the mass. We did that earlier. I'll just copy it down on my screen. So we found the mass of that object was this negative 1 over 2e squared plus 1/2. So that came from our previous example. Now we're going to compute our moments of mass with respect to x-axis and y-axis. And so I just jotted down those formulas from the previous slide to remind me of what we're doing. And so I'll start by finding my moment with respect to the x-axis. So I'm going to be integrating y times my density function, which was 2y. And I want to integrate it over the exact same region we worked with in the previous example. So just to remind you, you can go back or look at your notes. I'll try to draw it really quickly. Hopefully that's not too sloppy. So there's our e to the negative x. There's our x equal 1. And so, oh, I did not mean to erase all of that. There we go. So the region we're talking about is this region right here. And so my bounds of integration should be the same as what I did in the previous example. We're integrating over this region. So our y values are going from e to the negative x. That's our upper bound of our y values. Lower bound would be 0. And then the x values start at x equals 0, stop at x equal 1. So these should be the same bounds of integration that we used when we computed the mass. All right, so we have to integrate this 2y squared with respect to y. We'll do that first. Antiderivative of 2y squared is 2y to the third over 3. And then I'm going to plug in those bounds of integration. So I plug in the e to the negative x. I get 2/3 e to the negative 3x. And then technically if we plug in the 0, it's minus 0. So I won't write that down. All right, so there's my inside integral. And then I'm going to integrate 2/3 e to the negative 3x with respect to x. So I get 2/3 e to the negative 3x and then divided by negative 3. So let's see, that would be negative 2/9 e to the negative 3x. I'm going to plug in my bounds of integration, so I'm going to plug in 1. And then I'll plug in 0 and subtract them. And so I can put this in a calculator if I want. I'm just going to rewrite it as negative 2 over 9 e to the third. And then e to the 0 is 1, so plus 2/9. So this is my moment of mass with respect to the x-axis. We can use this to find the y-coordinate of our center of mass. To find the y-coordinate of our center of mass, we're going to take this moment with respect to the x-axis, and we're going to divide it by the mass. And so now I finally did pull out my calculator, put all of that into my calculator. I got approximately 0.4884, and so that would be the y-coordinate of my center of mass. All right, we are halfway there. Now we're going to find our moment of mass with respect to the y-axis. And so I'm going to integrate using my formula. I'm going to take x times my density function, which was 2y, and I'm going to integrate that over our exact same region. So bounds of integration are the same as what they were before. The y values go from 0 to e to the negative x. The x values go from 0 to 1. All right, but different function that we're integrating. We're going to integrate 2xy with respect to y. So I get 2xy squared over 2, or just xy squared. There's my antiderivative. And then I'm going to plug in my bounds of integration. So I'm going to plug in the e to the negative x, plug in the 0, and subtract them. When I plug in 0, I should get 0. And so this just becomes x e to the negative 2x. So that's what I'm going to have to integrate with respect to x e to the negative 2x. Let's see, this is a product. Technically, there's not a product rule for antiderivatives, but the technique I use to deal with products like this is our integration by parts. So I'm going to let my u equal the x, and I'm going to say dv is e to the negative 2x dx. So du, the derivative of u, is just 1 dx. And then the antiderivative of my dv, so my v would be an e to the negative 2x divided by negative 2. I'll call that negative 1/2 e to the negative 2x. All right, so using integration by parts, the formula is basically when we integrate u dv, we should get u times v minus v du. So let's see, that would give me u times v, so negative 1/2 x e to the negative 2x, and then minus a minus, so that's how I got a plus antiderivative of 1/2 e to the negative 2x dx. All right, so I think I set that up correctly using my integration by parts. So let's see, we've got negative 1/2 x e to the negative 2x, and then antiderivative of 1/2 e to the negative 2x. We're going to divide by negative 2 again. So now I've got a minus 1/4 e to the negative 2x. So all of that is my antiderivative. And now I'm going to go ahead and plug in those bounds of integration. So I'm going to have to plug in the 1. So I went ahead and plugged in 1. Negative 1/2 e to the negative 2 minus 1/4 e to the negative 2. And then I'll plug in 0. So I end up getting just 0 minus 1/4. And then I'm going to go ahead and subtract those. And so hopefully I haven't made any mistakes yet. This is what I got, negative 3/4 e to the negative 2 plus 1/4. This is my moment of mass with respect to the y-axis. And so to finish this problem, to get the center of mass with respect to the x-axis, I'm going to go ahead, and take my moment of mass and divide by the mass. I finally put all that into my calculator and got approximately 0.343 0.35 when I did that. Now, we can also use integrals to compute moments of inertia, and this is another topic that you'll probably discuss in a physics class. The moment of inertia of an object describes the tendency of the object to resist a change in rotation. And so I have a bunch of formulas written down on the screen. I've got moment of inertia with respect to the x-axis on the top. We'll be integrating y squared times our density function over the area of the region. Our moment of inertia with respect to the y-axis, we're going to be integrating x squared times our density function over the area. And then finally, this I sub 0 is our moment of inertia with respect to the origin. And that's going to be the sum of our I sub x and our I sub y. Or I guess if you add those two integrals together, you get x squared plus y squared times the density function integrated over area. So these moments of inertia, again, are the tendency of the object to resist a change in rotation about the x-axis, about the y-axis, and then about the origin. Once again, I really want to focus on the computations. Really, the goal of this section is to give us some more practice in computing these double integrals and then eventually triple integrals. So let's do an example. Let's see if we can find all three of our moments of inertia for a triangular region with vertices at 0, 0, 4, 4, and 4, 0, with a density function that is rho equals the square root of xy. So first thing I'm going to do is draw a picture. So there's my triangular region. It has a vertex at the origin, another one at the point 4, 4, and finally one at the point 4, 0. So I've shaded in the region we're talking about. I am going to just kind of denote on my paper that the slanted line in our triangle is the line y equals x. It has a slope of 1. It goes through the point 4, 4. That's the line y equals x. So we'll keep that in mind when we're setting up our integrals. And then I also jotted down on the screen those definitions for our moments of inertia, so we can go ahead and do those computations. So moment of inertia about the x-axis, I'm going to integrate y squared times my density function over the area of the region that I've drawn. I decided to write my square root of xy as xy to the 1/2. That'll just help me find my antiderivative. As far as my bounds of integration, if I'm going to integrate with respect to y first, the lower bound, we're starting at y equals 0, and we're stopping on that line y equals x, regardless of where we are in this triangle. So my y values go from 0 to x, and my x values start at 0 and stop at the right side of this object, which is x equals 4, so 0 to 4. So that's the integral I'm going to compute to get my moment of inertia. And let's see, x to the 1, we have this x to the 1/2, y to the 1/2, that's our density function. So y squared times y to the 1/2, if I add the exponents, I get y to the 5/2. So I actually need to integrate y to the 5/2, x to the 1/2. So inside integral, we should get a y to the 7/2 divided by 7/2. So 2/7 y to the 7/2, and then times x to the 1/2. I'm going to plug in my bounds of integration, the 0 and the x. So if I plug in the x, I get 2/7 x to the 7/2, x to the 1/2. If I plug in the 0, I get 0. So I won't write that down. And then let's see, we can add the exponents. 7/2 plus 1/2 is 8/2. or 4. And so this simplifies down to 2/7 x to the 4th. And then I'm going to integrate 2/7 x to the 4th with respect to x. So 2/7 x to the 5th over 5. Plug in the 4, plug in the 0, subtract them. I got 20/48 over 35. That's what I got for my final answer for my moment of inertia about the x-axis. So I just copied that down over to the side. There's one of my answers. And then I'm going to go ahead and find my moment of inertia about the y-axis. So I'm going to set up my integral the same way. So my bounds of integration are the same because we're talking about the same region. So y values go from 0 to x values go from 0 to 4. The difference is we're going to now integrate x squared times our density function. X squared times x to the 1/2 is x to the 5/2, and then we have a y to the 1/2. We'll integrate with respect to y first. So let's see. We integrate the y to the 1/2. We should get a y to the 3/2 divided by 3/2. So that's how I got this 2/3 x to the 5/2, y to the 3/2. I'm going to plug in my bounds of integration, which are x and 0. Plug in 0, I get 0. So I plugged in x. I got 2/3 x to the 5/2, x to the 3/2. Add the exponents, and this simplifies down to 2/3 x to the 4th. And then to finish, we're going to integrate the 2/3 x to the 4th with respect to x. So 2/3 x to the 5th over 5. Plug in the bounds of integration. Plug in 4, plug in 0, subtract them. I got 20/48 over 15. So there's my moment of inertia with respect to the y-axis. And then finally, moment of inertia with respect to the origin. I can just add those two moments of inertia. Feel free to pull out your calculator. I got approximately 195 when I added those two together. And so now I have found all three moments of inertia that we've talked about. All right, I think I have just one more example. The last example I want to do is going to show that these ideas can be extended to objects in 3 dimensions. So far, in all of my examples, we've been working with these laminas, which are these very thin objects like pieces of paper, so objects that we draw in 2 dimensions. But we can talk about objects in space as well, and we can actually find mass and moments of mass, moments of inertia as well. The only difference is we'll be integrating over volumes instead of over areas. And so the example I want to show you has to do with finding the mass of an object in space. So we are going to find the mass of the cylinder. X squared plus y squared is less than or equal to 9, where the z values go from 0 to 5. And its density function is rho equals z. So I'm going to draw my object. So we are talking about a cylinder oriented along the z-axis that has a radius of 3. So x squared plus y squared equals 9 is a circle with a radius of 3. And the z values start at z equals 0 and it stops up at z equal 5. So that's the object we're talking about. To find the mass of this object, we are going to integrate our density function over the volume. So we're actually going to set up a triple integral. My density function is just z. That's what I'm integrating. And my z values start at 0 and stop at 5. Okay, so there's the dz. That's not too bad. And then we could set this up with a dy and a dx. So we could set this up with the dy and the dx. And think about this in the projection in the xy plane, which is just that circle. Although, I think in this case, because we're dealing with a cylinder, it's actually going to be a little bit easier to work in cylindrical coordinates. If we wanted to work in rectangular coordinates, again, just to clarify why the cylindrical coordinates are easier, if we wanted to work into rectangular coordinates for our dy dx, we'd be looking at this circle that I've shaded in purple, the projection in the xy plane. That's the equation x squared plus y squared equals 9. And so our y values would go from negative square root of 9 minus x squared to positive square root of 9 minus x squared. The y values would be going from the bottom of the circle to the top of the circle. These expressions are kind of ugly, and that's why working in cylindrical coordinates is going to be a bit easier. So rather than using a dy dx, I'm going to change that to an r dr d theta. Okay, so always need that extra r in there. My dy dx is going to become an r dr d theta. All right, I don't have to do anything with the dz. Z in cylindrical coordinates is the same as the z in rectangular coordinates. So my z values still go from 0 to 5. But now, if we're thinking about this circle in the xy plane, in our cylindrical, or I guess in 2 dimensions, it's like thinking about it in polar coordinates, the r values, the radius of this circle, again, that I've shaded in purple, radiuses go from 0 to 3, and the thetas, if we go all the way around this circle, our angles are going from 0 to 2 pi. So those are our bounds of integration. And this is a much easier integral to do because you notice that when we put this in cylindrical coordinates, our bounds of integration are all constants, and that's going to make the work a bit easier. All right, so we are integrating this z times r, and we'll do it with respect to z first. So z times r integrated with respect to z, I get z squared over 2 times r. I'm going to plug in my bounds of integration, which are the 5 and the 0, and that simplifies down to 25 over 2 times r. So now I'm going to integrate my 25 over 2 times r with respect to r. I get 25 over 2 times r squared over 2. So that would be 225 over 4. All right, and then finally, I'm going to integrate 225 over 4 with respect to theta from 0 to 2 pi. So I get 225 over 4 times theta, and that simplifies down to 225 pi over 2. And that is my final answer. That would be the mass of this cylinder with the given density function. All right, so that is it for this section. As always, let me know if there's anything I can clear up from this video.